Welcome back, and let's continue the discussion on the modeling part. So, we are looking at the difference model like Grant-Smith model in the two equation, and this is what we looked at the turbulent kinetic energy term, where you can see this model equation for the K. Now, when you look at the, this is for unsteady equation for the K, where if you look, this is the term which is rate of increase, this is the convective transport, this is diffusive transport, this is production and rate of destruction. So, here the Prandtl number sigma k, which connects the diffusivity of k to the eddy viscosity, typically value is 1 is used. So, that is the typical value is 1 which is used. Now, we can look at the turbulence dissipation. This will look similar to K, look similar to K equation, but one has to note that K equation mainly contains the primed quantity, indicating that the changes in K are mainly governed by turbulent interactions. And also, but in the viscous dissipation there are terms which will be coming from the component due to viscous stresses and like that. So, we have to define the dissipation as 2 nu epsilon ij prime. So, this is per unit mass, because this is quite important. Now, if you look at the complete expression for the epsilon equation, this is the analytical equation for the epsilon. So, if you look at that, this is quite complicated, or rather apparently it looks quite complicated and it cannot be solved that easily. So, this is your unsteady, this is convection, this is a term, you have production, these. So many terms are involved here. Now, that is why the simple equations which are used to solve for. So, the model equation which is usually solved, this is the unsteady term, this is the convective transport, this is your diffusive transport, production and destruction. So, this is the simplified version. So, this is how we derive by multiplying K equation by epsilon by K. So, this is an very commonly used epsilon equation, where this coefficient C epsilon 1 is 1.44 is commonly used, C epsilon 2 is 1.92 and sigma epsilon typically used 1.3, which is again the number, Prandtl number connects the diffusivity to the eddy viscosity. This connects diffusivity to eddy viscosity. Okay. Now, we can calculate the Reynolds stresses from K and epsilon. So, our eddy viscosity is approximated like C mu K square by epsilon, where C mu is 0.09 and the Reynolds stress is mu t del ui by del xj plus del uj by del xi minus 2/3 k rho delta ij, which is nothing but 2 mu t eij minus 2/3 rho k delta ij. Now, if delta ij is 1 for I equals to, basically I equals to j, and this is 0 rest. So, this 2/3 by rho k delta ij, this term, this is the normal stress which sum to k, but one has to note that K epsilon model leads to all normal stresses being equal, which is usually an inaccurate Now there are advantages, there are disadvantages. So the advantages: simple to implement, leads to stable calculations and converge relatively easily, stable calculation, then reasonably good prediction, reasonable predictions. But if you look at the disadvantages, this is absolutely provide you poor prediction for swelling and rotating flow, flows with strong separation, axisymmetric jets. So doesn't work essentially for swell flow, strong separation, axisymmetric jets, unconfined flow, some unconfined flows, fully developed flows with, but it is quite valid for fully turbulent flow and simplistic epsilon equation. So there are other brand of epsilon models which are K epsilon, RNG K epsilon, we have realizable K epsilon, we have K omega model, we have algebraic stress model and also nonlinear model. So these are some of the other models also comes under the banner of two equation models. Now what is the improvement of RNG K epsilon? So there is a K and epsilon equations are derived from the application of rigorous statistical technique which is called renormalization group method to instantaneous Navier-Stokes equation. So the equation looks similar to K epsilon equation, but it includes some additional term in epsilon equation for interaction of turbulence and dissipation mean shear. So it takes into account the effect of swell. So analytical formula. So it provides you some improved prediction for high streamline curvature and strain rate, some transitional flows and wall heat and mass transfer, but it still does not predict the spreading of round jet correctly. So if you look at this RNG K epsilon based equations, so this is my convection term, generation term. So this is again for steady incompressible flow, this is diffusion, and this is the epsilon equation where additional term related to mean strain and turbulent quantity. So this is what comes into the picture when you compare to standard K epsilon. Now there is another group where the realizable K epsilon, this is improved, this actually a improvement. So this improves performance for flow, Ilvoni planar and round jet, rotation and recirculation. So boundary layer undergoes strong boundary layer with adverse pressure gradient, and also for strong streamline curvature. So these are the improvements which actually there for the realizable K epsilon model. So some of the from the standard K epsilon model this deviate, and the one of the major deviation is that the estimation of the turbulence eddy viscosity, which is mu t is calculated C mu K f square and C mu is looking like that. Here it ensures positivity of the normal stresses, that is number 1. Number 2 also it ensures the squares inequality. So, the dissipation rate equation has typical diffusion, generation, this is the destruction term is modified and also the effect of buoyancy. So, if you see there is a quite a bit of improvement which takes place here for the realizable K epsilon model. Now, here the model constants are estimated, like mu t is estimated with a model constant C mu and K square by epsilon, where C mu takes care of this effect, it is not constant anymore. Then where U star takes in the both the strain and the rotation part. So, this is rest of the parametric constant. Now, if you look at the Bouguereau's hypothesis in this, so the normal components are estimated like that in the realization K epsilon case, and this would be negative if this is greater than. So, these are some small. Now, the other set of model is the K omega model. So, this is another 2 equation model. So, this omega is the turbulent frequency. So, this solves for 2 equations, one is the K and another equation for omega, and here the mu t is calculated as rho K by omega. So, its behavior is similar to standard K epsilon model, but it has some drawback, that here this mu t assumption is isotropic, which is an huge drawback of this particular model for the application in large scale problem. Now, the other set of model is the algebraic state stress model. This is same K and epsilon equations which are solved with standard K epsilon model, or standard K epsilon model, but Bouguereau's hypothesis not used here. Now, full Reynolds stress equation are first derived and then some simplifying assumptions are made to allow derivation of algebraic equations for the Reynolds stress. So, have fewer PDEs compared to RSM, and also it is quite easier to implement compared to RSM. So, these algebraic equations and are not very stable, however, computer time is significantly more than the standard K epsilon or K omega model. So, this was used in old days, but once the RSM model is available, so this is not very often used. Now, then the another set of correction is the nonlinear corrections, which is standard K epsilon model is extended by nonlinear corrections, where your Reynolds stress term, this is an example of Spezile model, where this f is a complex function, this is an complex function of deformation tensor, velocity field and gradient and the rate of change of deformation standard. So, the standard K epsilon model here reduces to a special case of this model and low Reynolds number of deformation. So, these are relatively new because these nonlinear corrections which take into consideration, but then using these nonlinear corrections there is another advancements which has been taken place is the development of hybrid models, which uses both RANS plus LES. Now, this is a Reynolds stress transport equation, this is where we have already looked at it. Now, you solve for individual stress term. So, it becomes quite computationally expensive, and this is also complex in nature, but it includes the effect of streamline curvature. So, it includes effect of streamline curvature, sudden changes in strain rate, secondary motions, and all these can be taken into consideration. So, these are the terms which are actually associated with that. This is a generation term, the turbulence generations are given like that, and this is pressure strain term, this is dissipation and the diffusion term. So, this is again we are looking at the, now this this is based on Rand's averaging. You have 6 Reynolds stress equation which we solve. So, these transport equations are derived and these are solved. So, result equation, so there is why no Boussinesq hypothesis is required. This is good for predicting complex flows. So, it accounts for the streamline curvature, swell, rotation, high strain rate. So, this can be used in combustor calculation, cyclone flows, rotating flow passages, secondary flows, flows within separation. So, this is an quite a bit of improvement, and the exact equation looks like is that Pij plus Dij minus epsilon ij plus ij, where this is the rate of change, and this includes rate of change plus transport of Rvj, this is production, this is diffusion, this is rate of dissipation. So, this is turbulent pressure strain interaction, and this is the rotation. So, these are the component which actually takes into account. So, production, dissipation, production, diffusion, dissipation, pressure strain and the rotation. So, production is retained in its exact form, some comment about that. So, diffusive transport modeled using a gradient diffusion assumption, that is another aspect of it. The dissipation epsilon aj, this term is related to epsilon and calculated from the standard K epsilon equation. The pressure strain interactions are quite important because this include, so this actually includes pressure fluctuations due to eddies interacting with each other at different mean velocity. So, the overall effect to make the normal stress more isotropic and to decrease the shear stresses. So, it does not change the total turbulent kinetic energy. So, this is one of the term which is very difficult to model, and various models are available. Common is the Launder model, improved nonlinear, and finally, this term is the transport due to rotation. So, your production is quite exact, as we said, which one can write that Rjm by, and the diffusive transport is also Ijk by del xk. Jik is nothing but I prime uk prime plus p prime delta jk ui prime plus delta ik uj prime. Diffusive transport model Dij is del xm by nu t by sigma k del Rij by del xm, divergence of nu t by sigma k grad Rij, where nu t is the turbulent kinetic viscosity and calculated in standard way. So, also the dissipation is exact, so one can approximate that del u prime by del xk uj prime by del xk, where dissipation model uses is 2/3 epsilon delta ij. Pressure strain term which is minus p prime del xj plus del uj prime del xi, and there are models available, and rotation term is minus 2 omega k Rjm Ekm plus Rim Ejkm, where this is minus 1, 0 or 1 depending on the situation. So one has to set up the boundary condition. So you need to characterize the turbulence at the inlets and outlets. So K epsilon models require K and epsilon, Reynolds stress model requires all the other options, turbulence intensity and length scale, where the length scale is related to the size of large eddies. For boundary layers 4, one can define that length scale for other flows, then also turbulence intensity and hydraulic diameter, or one can use the viscosity ratio. Now if we put these Rans based models together, then one can see this is Spalart-Allmaras model, standard K epsilon model, RNG K epsilon. So these are the improvement, standard K omega, SST K omega. So these are different variable Rans model which are put together, and what is the behavior? One is very simple, used for, it has certain advantages that we have discussed. So depending on their advantages and disadvantages, one has to use it. This is quite involved, it can take care lot of the other aspect of it. So if we look at the sum of the basic strength and weakness of these models, if you look at SA model, it is economical, good track record for mildly complex boundary layer flow, but not very widely tested. Standard K epsilon, robust, reasonably accurate, long but mediocre results for complex flows, it does not take into account swell, rotation. RNG, it is good for moderate behavior like jet impingement, separating flows, it has also certain limitations. Realizable K epsilon, this is quite good modification to the standard model, and it is subject to limitation of the isotropic eddy viscosity assumption. It is more complex model, but requires more CPU time, so it is tightly coupled with the momentum. So one another important aspect when you look at the boundary layers or wall bounded flow, you need the near wall treatment. So this is a special treatment required to mean flow field, is a standard wall function, non-equilibrium wall function, or 2-layer zonal wall function. So if you look at the wall profile which we have discussed, this is our viscous sublayer in the boundary layer, the buffer layer, this is fully turbulent zones, or this rather can be totally inner layer, and this is outer layer. So you need near wall modeling for engineering application because of the drag, pressure drop, separation, all these are important aspects which require. So most of the problem in the inability to resolve the epsilon, so we require some treatment, either standard wall treatment. So SA and K omega models are capable of resolving the near wall flow provided near wall mesh is sufficient. That means if you resolve the mesh, so that means if you look at this is the buffer layer and this is zone and this is the inner layer and outer layer. So it is depending on the mesh resolution one can. So the wall function options, the standard and non-equilibrium wall functions which are set designed for high Reynolds number flow. So there is a viscosity affected, near wall region is not resolved, so near mesh resolved is relatively coarse and empirical based model. And if you go by essentially enhanced wall function situation, then it is used for low Reynolds number flows or flows with complex near wall phenomena. This is requires fine near mesh capability and modified at the inner layer. So these are the some of the standard wall function which is quite often used, and by using Launder-Spalding law, that U star is Y star, U star is this, the depending on the Y star definition. So this is similar to wall laws. Additional formulas account for K epsilon and Reynolds stress. Less reliable when the flow departs from conditions assumed in their derivation. So that CBR delta T P is non-equilibrium wall function. So this is modified, standard wall function is modified. This is SWF for stronger delta P and nonlinear flows. This is also less reliable for high transportation or body forces. So these are the options one can use for K epsilon and RSM based turbulence model. Now this is enhanced wall treatment. So where your momentum boundary layer is blended, similar blended wall laws, and then pressure gradient effect, thermal effect, these are what is taken care of. and if you go for 2-layer model, where this blended 2-layer model is used to determine the near epsilon field. So, the domain is divided into near wall region and the turbulent core region, where wall distance, and so this has a high Reynolds number turbulence model. So, the enhanced wall treatment near wall model are options again for K epsilon and RSM turbulence model, where one can use it. So, any of these CFD packages or the commercial packages that is available that has this kind of wall treatment that one can use. This is estimating the first grid point, because once you use the wall treatment, then you have to estimate your first grid point or the size of the grid point, so that you estimate. So, the details you can find it any turbulence book or any turbulence modeling book, that what would be the value of y plus. So, this is a critical parameter that one has to look at it when they. Now, if you go by the some of this recommendation, so one can use the standard wall function or near non-equilibrium wall function for most high Reynolds number applications, which cannot afford to resolve the viscous sublayer. That because Reynolds number is so high, we cannot resolve it. There is little gain resolving viscous sublayer, use non-equilibrium wall function more mildly flows, but you may consider using if the characteristics R is low or if near wall characteristics need to be resolved. So, this is some cases one can. So, the physics and near wall mesh of this case is such that y plus is likely very significantly over this. Now, then at the same time you need to set the boundary condition. So, obviously one has to provide boundary condition for K, epsilon and other stuff. So, if you put the summary of these guidelines, so successful modeling requires flow physics, computational resource available and the requirement like accuracy and turnaround time. So, then you can depend on the model and near wall treatments available. So, you calculate the characteristics of RE, estimate wall adjustment depending on the y plus, you can use some standard K epsilon, then move to other advanced model or use some RSM and use wall function. So, these are some of the summary, which is modeling various degrees of complexity, where these are RANS based models are used often for the engineering problems, and if you want to be captured everything, then go for DNS or RSM kind of. So, that talks about pretty much what kind of modeling which is required for engineering problem or the small scale problem and the issues. So, then we will stop here and start our discussion on the turbulent reacting system in next lecture.